Yeah, this panel, I can move it down. Yeah. So, good afternoon to everybody. We are going through various sessions, and now we are primarily discussing the antennas. You had yesterday a full session on the basics of antennas, and then today you learned about arrays, how to make arrays. Now, one thing is that antennas do find application in the user equipment, but more so in the base stations, because this is where the major installation of antenna takes place. And we are going to discuss a little bit about these base station antennas, how they function, on what basis they are designed. So I will be talking mostly about the cellular communication, the base station antennas used for cellular consideration and some of the design considerations. Wi-Fi and WPAN system, they also do use base stations, Wi-Fi base stations and all, but these are not very complicated antennas. So let us proceed. So what is a base station antenna? That carries multiple signal channels. As you know, in the wireless communication system, we have large number of channels through which the communication takes place, and each channel actually will consist of essentially two frequencies, the uplink and the downlink. While the user equipment is to work on a pair of such frequencies, a base station will have to handle all these large number of channels. So base station antenna carries multiple signal channels and has an antenna pattern that covers some defined region around the base station antenna. So the coverage that you get from a particular base station, that is determined by the antenna present in that base station. And many a time when we use the mobile phones, we switch from one base station to another base station, which is called a handover process. Many times it is not transparent to the user, so user do not feel the point of attachment has changed. So base station also houses this complex circuitry for doing that. And as you have seen that these base stations antennas, these are placed at higher altitudes, usually at a height of 10 meters to 20 meters uh, on a platform, so that it can give wide coverages. And these base station antennas are repeated after certain distances. Today, you go to any uh, city, be it a small or a large city, you will see lots of base station antennas, and at places you will find multiple operators put their antennas. So base station antennas, these are operated by the operators, telecom operators, wireless service providers. And many of these base station antennas and other things, they use equipment which are proprietary. Therefore, not much discussion is seen. So we thought that in this session we will try to at least give some overview of how these base station antennas function, on what basis they are designed, what are the parameters that are needed to be considered when you design this type of an antenna system. So base station antennas, it control the frequency use and optimization of channel capacity for a mobile radio network. This is very, very important because the operator, they want to put maximum number of users with a given number of channels, and how antenna can help that. That is, so typically, if you consider base station antenna types to start with, when initially mobile communication started, people used omnidirectional antennas. And omnidirectional antennas, as you can understand, it has coverage in all directions. Omni in the sense that it is omni in the uh, azimuthal plane or the horizontal plane it tries to cover, and of course in the vertical plane or the elevation plane that will be restricted because we have most of the users located uh, at either at heights lower than the base station antenna or at heights comparable with the base station antennas. At very high elevation angle, the number of users will be very less. Omnidirectional coverage was used in the initial period, and then you know that we use cellular structures and we use hexagonal cell, and if you consider the center of an hexagon, it is almost like covering that of a circle. Hexagon is used for designing the system so that you have a tessellating structure and you do not have any void left in between. If you use circles, there will be voids left in between. And this is a very standard geometry used in the design of wireless communication systems, cellular systems. So hexagonal geometry has become very, very common. And the center of the hexagon, you will place an omnidirectional antenna. But later, people found that there is benefit in splitting this hexagon into sectors. So, for example, centered, if you take a hexagon and put 120-degree centers, then you split the hexagon into three parts. So this sectored antenna became very popular after the second generation of the cellular deployment. And then 3G onward, people have started talking of adaptive antennas or smart antennas. The difference is that in sectored antenna also, antenna particularly serves the sector under its control. When it comes to adaptive antennas, beamforming antennas, or smart antennas, many terminologies are used. These are the antennas where you can actually change the beam location, you can create multiple beams, you may put, the ultimate is that you can put one user in a narrow beam. So this is what, and you can actually increase the range, decrease the range of the coverage of the base station by controlling certain parameters in the antenna design. So smart and adaptive antennas, these are also uh, uh, used in today's base station, these concepts with varying degree of application and flexibility. And if you notice the uh, literature, people will always mention that, okay, base station can do this, base station can do that. So it is assumed that base station, you can put more complexity, and it is quite logical because in the user equipment, you have the limitation of the space, and putting multiple antennas in a small handset equipment becomes very, very challenging. Whereas these challenges are not much there in the base station antenna design where you can put multiple number of antennas. So we actually shift the complexity, design complexity many a times on the base stations. So this is the picture of a base station type of antenna, which you will commonly see today. If you look at any tower, you will have this type of structure, and you can see that if you look carefully, it is not kept vertical, it is kept with a angle, and some mechanism is there by which you can adjust the tilt of these. So this type of rods, they will be looking towards the ground with at an angle. We'll see those why it is done so. And similar type of systems are also there for the Wi-Fi base stations and these things, particularly which are used in the campus networking and all. You will have some wall mount systems, the smaller units, and you can have the flexibility of tilting them, directing the beam towards certain direction. So all these facilities will be there. So what are the parameters we look into when somebody wants to design base station antennas? What are the parameters that are to be taken into consideration? This is very, very crucial because from an antenna designer's point of view, what challenges they are going to face, that will be determined by those parameters. So major parameters, first is the frequency range. So you know that today wireless communication is taking place at different frequency ranges. Uh, GSM, initially it was around 900 megahertz. Then we moved towards 1800 megahertz. Then in the sub 6 gigahertz range, around 3 gigahertz activities are taking place. IoT, the long range ones, they are going down to the megahertz ranges. For example, 860, 870 megahertz, these frequency ranges. So again, on the higher side, yesterday we discussed about millimeter waves. So 28 gigahertz, 39 gigahertz. So these are the frequencies. And definitely, as you move higher up in the frequencies, your wavelength is becoming smaller. And as we have seen that antenna design, everything becomes very critical. And also the lower frequencies, same way. One good thing about the base station antennas is that the scaling of the antenna to the size of the transceiver equipment, this is not as stringent as that of user equipment, because user equipment, you cannot have a very large size antenna and a very small transceiver electronics. They are to be very much compatible. Base station has this flexibility. You can have larger dimensions of antennas, you can put bigger arrays, but there are other considerations. So first of all, the frequency range that this antenna will cover, this is very, very important. And there are, if you search for the data sheet of the base station antennas, you will find plenty of solutions. People have developed base station antennas covering all commercial frequency bands in which the mobile communication takes place. The next is the gain. So gain, yesterday somebody was asking me how I can improve the gain of my antenna and these things. So two terminologies which we use very often, uh, they are very close. One is the directivity function or directive gain, and another is the gain of the antenna. There is some differences. Directivity function you calculate totally on the basis of the radiated power. It is the power radiated per unit solid angle. I repeat, it is the power radiated per unit solid angle divided by the power that is average power radiated per unit solid angle. So suppose your antenna, it radiates a power PR. So if it is radiated uniformly in all directions, the total solid angle around any point is 4 pi, so it will be PR by 4 pi. So the denominator term is PR by 4 pi. And power radiated per unit solid angle, we normally denote by dPr by d omega. So dPr by d omega is the power that is radiated per unit solid angle, and solid angle, you know that it is the area on a sphere which subtends area which is equal to r square, which subtends the angle at the center of the sphere. So the ratio of these two, dPr by d omega divided by PR by 4 pi, that will give us the directivity function d theta phi. So this directivity is going to be a function because you are finding out power radiated per unit solid angle that will vary with theta and phi. I hope yesterday when we discussed the basics of antennas, these were discussed in detail. I'm just repeating the some of these. So d is a function of theta and phi, and directivity is the maximum of this directivity function. Now, when it comes to gain of an antenna, when we say the gain of an antenna, gain is not defined in terms of the radiated power, it is the input power. So 4 pi into dPr by d omega by P input. And here comes, because not all the input power is radiated, then where does it go? So the power is lost within the antenna. If it is a metallic antenna, it will dissipate some power. The metal will have finite resistivity, and you will not get all the power that is given input to the antenna as radiated power. And therefore, we talk of another term which is called the radiation efficiency, and which is, if you are designing a very highly efficient antenna, this efficiency will be say about 0.95, 0.99, 0.98, like that. So if you multiply the directivity function by that efficiency of the antenna, that will give you the gain function. And gain function is again a function of theta and phi, and maximum of that we call the gain. If you have a directive antenna, the direction in which the maximum radiation takes place, and if you measure the directivity function and multiply it with the efficiency of the antenna, you will get the gain in that direction. So gain of the antenna, and this is usually specified. Then comes the beam width. Beam widths, we talk of two types of beam widths. One is 3 dB or half power beam widths, and another is first null beam width. Both definitions are used, and usually most commonly used one is the half power beam width, practically one, where the power reduces to half its maximum value, and beam width may be in the azimuth or it may be in the elevation plane. So horizontal to ground, and if you considered vertical plane to the azimuth, then you get the elevation. So you talk of 3 dB beam width, and this beam width is going to play an important role, we will see. What are the other parameters? Down tilt. I showed you the picture, and we saw that our antenna, which is the antenna which I showed, essentially is an array antenna, and it is put inside some cover. So these are called radomes, and these are also to be designed because they should be transparent to the radio signals, but they will provide adequate protection. So cover design, it's not antenna radiating in free space. So these structures, they are tilted slightly, and this is the down tilt angle, and how this is important and how it is decided, that we will discuss later. Then maximum VSWR. You know that the signal will come from the electronics, and this signal, how good it is matched to the antenna system, that will be determined with the VSWR. Very low VSWR, we want the VSWR to be, say, ideally 1, no reflection. Practically, if a VSWR is of the order of 1.1, it is a very good match. Even more relaxed is VSWR 2, which actually equal to a reflection coefficient of 1 by 3, and that means the 90% power actually goes inside, transferred to the load, and only 10% is reflected. So in that way, VSWR is a parameter which needs to be found out, and over the entire band of frequencies. That's why any antenna design, what we do the VSWR measurement over the band of frequencies, and we want it to be as flat as possible over the operating band. Then comes the polarization of the antenna. Now, different types of polarizations are used. In some cases, it is linear polarization, purely linear, and then you have dual polarized. In fact, you can have the antennas operating, radiating in two polarization, X and Y polarizations. You can have circularly polarized. So different types of, in general, it is elliptically polarized is the general case. And if you have a phase shift between the two orthogonal polarization of 90-degree, they are in space quadrature as well as in phase quadrature, then we get circular polarization. So what type of polarization is being used? This is also important. Cross pole isolation. So suppose you are transmitting and receiving, agreed to transmit and receive in the vertical polarization, then how much you are receiving in the horizontal polarization, that gives you the isolation. And ideally, you do not want to receive, if it is vertically polarized, we do not want to receive in the uh, horizontal polarization. But in practical cases, it will pick up some signals with horizontal polarization also. So that will determine how much cross-polar isolation it provides. Similarly, between circular left and right circular polarization. So this cross-polar isolation is another important parameter. Front to back ratio. If you are using a directional antenna, you want to transmit in a particular direction, and you do not want to transmit in the back side of the antenna. So front to back ratio, what is the minimum F by B is needed? That is another parameter when it goes. And if you consult the data sheet of an antenna, you will find all these parameters being specified by the manufacturer, and you have, depending upon the requirement, the service provider is going to provide to its customers. They will pick up the antenna from these available ranges, because all these parameters, what values that are determined during the network design, that I require a minimum of F by D ratio of 20 dB. Some people may be happy with 15 dB. Side lobe levels, again, what are the side lobe levels you are looking at? These are issues. And finally, the power. The base station power may vary. It may, and it will decide the range, and your antenna system should be able to transmit that much amount of power. So how much power you provide to the input port of your antenna, that is very, very important. And how much power it gets radiated finally. So it may vary from, say, 10 watts, 20 watts to as high as 100 watts, depending upon your base station antenna. And this is where many regulations come into picture. There are emission limits set by the international bodies that should not be violated. But the problem is, many a times when you have multiple base station radiating signals, and at a point the fields, they may add up, giving a local boost of power. So this power level has to be designed keeping in mind the regulation limits which a particular country follows. Uh, some part, FCC, ICI, NRP. So these are the bodies. They say that how much power you can radiate, and accordingly the base station power is chosen. So these are the electrical parameters I have discussed. Now there are, apart from these, in the base station antenna, you need to also consider some of the mechanical parameters, because as I told that this antenna will be mounted on a platform which is elevated one, maybe some 10 meters to 30 meters high platform, and many issues come into picture. The dimensions, what is the dimensions of the antenna? Then weight is another parameter comes into picture. Mounting, how it is mounted, how much mounting structure you require, whether you can mount it on a pole or you require some sort of other structures to be made for mounting the antenna, or it may be, in the case of a Wi-Fi base station, can it be a wall mount? Like that, mounting issues will come. And these are, mounting is also associated with another issue is serviceability, because the antennas often requires servicing. Wind survivability. The base station antennas are going to operate outdoor, and sometimes at very harsh conditions, the temperature ranges will change, and also there may be, they face, particularly in countries like ours, they face a lot of wind, or when in the coastal area, strong winds, they need to survive. We need to make provision for grounding, for lightning provision. So these are some of the mechanical aspects of uh, base station antennas which also need to be given due consideration. Let us come to other issues. Support for diversity system. So many a times the receive diversity, it is performed at the base station. We talk about the receive diversity, but you can easily have multiple antennas at the base station, whereas the mobile station, you will have one antenna, and if you are going for more than one antenna, that number also will be limited. So diversity, spatial diversity, receive diversity system, combining, or polarization diversity, all these things, this support for diversity system has to be there. The base station arrays are also used to provide transmit diversity. I think this has already been discussed and ultimately leading towards MIMO. Other issues in the design, passive intermodulation products. Now, you have, nowadays we work with multi-carrier system. So when you have a large number of carrier frequencies operating close by, and if there is a nonlinearity is there, intermodulation products are generated. Please note that base station antenna is a transmitter. Any issues, Pubali?
No, sir.
Okay.
Yeah.
I am audible fully.
Yes, sir. Yes, sir.
Yeah. So the sinusoids, if you pass two sinusoids to a nonlinear device, for example, to a squarer, it will produce sum and difference frequencies. Now, a base station antenna system, it consists of a transmitter as well as receiving antennas also. So if it happens that when multiple frequency transmission encounter a nonlinear voltage current relationship, the result will generate passive intermodulation products. And this, some of these frequencies are likely to fall, if they fall in the receive frequency band, and they will cause interference. This may cause interference within the base station itself, or they will cause in some other base station or user equipment operating in other places. So these intermodulation products are very, very important parameters to be taken into consideration while designing practical antenna system. Let me now come to, we'll discuss this issue in some detail. Let me now come to sectorization. As I told beforehand, that initially it was the circular omni coverage region which was modeled as a hexagon, and later on this hexagon was even partitioned into sectors to increase the frequency reuse and also to improve the capacity. Now, usually there are two types of sectorization is used. The first one, you can see you have a group of hexagonal cells, and now you have rhombic cells. So if you put three antennas, one giving coverage to these, and another antenna giving coverage to these. So usually you will find a mast containing three arrays and forming the shape of a triangle like this. So if you have this type of an antenna, then the region you are going to cover, so if this is one antenna placed here, and this is an array giving this coverage, you are going to serve a region which is rhombic in dimension. You can see this is one rhombus, you will be served by one antenna. This is another rhombus, will be served by another antenna array, and another rhombus served by another antenna, and these three together will be put in the same pole and make a base station antenna. So this is one arrangement which is usually used. This is one solution. The other solution of sectorization is what is followed in GSM systems. It does not put antenna at the center of the hexagon. The base station antennas are put at the junction of three hexagons. So now you can see the antenna giving coverage to this hexagon is essentially serving to the entire hexagon. The other antenna located here will serve this hexagon, and the third antenna located here will serve this hexagon. So you will have again a sectoring, but now these your antennas are giving coverage to hexagonal geometries rather than giving to covering rhombic regions. So this is hexagonal cell in GSM created by placing base station at the intersection of three hexagon, and a base station will cover all these three hexagons by its array placed accordingly. Now, what should be let us continue with this structure, which is most popularly used, and let us try to find out what should be the beam width of the antenna that you will require, particularly in the horizontal plane, to give this type of a coverage. So what we can do, this hexagon can be thought of as a circle, superscribed circle to this hexagon we can think, and if this side of the hexagon is R, then what will be the diameter of this circle? It is going to be twice R. All right. So we know Friis transmission formula, and Prx is Pt lambda by 4 pi. We can write 1 by r raised to the power gamma, where gamma is the path loss exponent, will vary say from 2 to 4 depending upon the number of scatterers. Grx is the gain of the receiving antenna, and Gtx phi, this is the gain of your base station antenna at a particular angle. That's why I discussed this issue of gain to some extent elaborately again, to say that when you say gain, only gain, you mean it is the maximum of the gain function. Now, if we consider a coverage region like this, what will be the objective? We would like to see that, we know that if I put antenna here, the user equipment located in this region, they will be served very nicely. The problem will be with the user equipment placed along the periphery of this hexagon or along the perimeter of this, along the circle. And we want to give them a constant coverage by appropriately designing a beam. So, as I told that this distance now can be written as 2 R0 cos phi, where the phi is the angle measured with respect to this. Now you can see that when phi is equal to 0, you have this dimension 2r. When phi is equal to 90 degree, r is 0, and in between the any point on the circle, you can represent it by r phi is equal to 2 r0 cos phi, and r0 is the length of the side of the hexagon. And if we want constant radiation intensity, because if we can maintain at least constant radiation intensity over the cell border, and then we get the following condition: Gtx, because Grx we are assuming constant, lambda by 4 pi is decided by the operating frequency. We are transmitting some amount of power and we are receiving this power. So this Prx can be made constant provided Gtx phi by r to the power gamma, this can be made constant. And that means Gtx phi by 2 r0 cos phi raised to the power gamma is constant. And with this, you will get the half power beamwidth. If you solve it, it is 2 times cos inverse half raised to the power gamma, and depending upon the value of gamma, for example, with gamma equal to 4, you will get half power beamwidth to be 65 degree. For gamma is equal to 2, you will get the half power beamwidth to be 90 degree. So now this becomes the challenge for us to design an antenna, say with 65 degree or a 90 degree half power beamwidth, and so that we get the coverage uniform across the periphery of this circle. This I am showing the diagram of a omnidirectional antenna, and when you use an array, you will get a main beam with side beams, side lobes, and notice here we are showing a tilt angle here. And this tilt angle is important. How do you decide about this tilt angle? And by appropriate phasing of the elements, you can actually design this tilt angle by changing the phase of the excitation of the elements of the array that you are using in the base station. So otherwise it is having omni coverage in the azimuth. Elevation plane, its beam width is very small, few degrees, usually 10 to 15 or 20 degrees. But this beam is not symmetrical about this horizontal line. This beam is tilted by some degree. Here it is shown say 7 degree. It depends upon the requirement. So elevation radiation pattern for an omni base station with a tilt, and tilt angle by which the elevation pattern maximum is placed below the horizontal is known as the beam tilt of the antenna. Now, how you can provide this beam tilt and why it is needed? How beam tilts help? So, if you look at the fall of power with distance from a base station, the limiting radius of the cell represents the distance at which, so this is the cell as D1, there is reasonable chance that the SINR will be sufficient to provide adequate coverage. Sorry, I think I missed the word coverage. Adequate VER. So this is this distance. Up till that distance, you get adequate VER. And beyond this, the usage of the same frequency will not be possible because of the mutual interference. Because some other cellular station will be there, it is also transmitting, so both the signal will be there. And at a sufficient distance, the signal level has fallen. So when you go to the second level, this is the first level, maximum useful signal level. This is the acceptable level for interference in the neighboring cell. And at this distance, D1 and D2, the signal has reached a level where the same frequency can be reused here. Signal level has fallen through another cell to reuse the same frequency. The elevation beam width of the base station antenna is typically few degrees. By tilting the beam downwards, significant reduction in reuse distance is possible. Now, this distance actually can be reduced to a considerable extent because this is where we have this interference, high interference region. It can be reduced by using the tilt. So mechanical tilt is provided by angling the base station physically downward. I showed in that picture. The antenna unit itself is put with a tilt. Whereas electrical tilt is provided by controlling the phase of the radiating element. In order to define the average coverage of the base station, antenna is often mechanically tilted, and mechanical tilt distorts the footprint. Electrical tilt was therefore introduced since radiation from antenna is then directed towards downwards by means of excitation of feed network. Mechanical tilt, it is provided simply by placing the antenna element, and you can have some adjusting these things by which you can adjust the tilt of the antenna. Electrical tilting is by changing the phasing or the feed network, you can adjust accordingly and you can provide the tilt. So this is how the two looks at. This is the case with the mechanical and this is with the electrical. And as it is mentioned that the mechanical tilting often leads to the distortion of the beam Whereas electrical tilting, the beam shape can be, coverage shape can be maintained. So to make the tilting even more efficient, remote electrical tilt, RET, is a technology which was launched in early 2000. What happened? Mechanical tilt means somebody will have to climb to the base station, they will adjust. Electrical tilt also, you will have to have the phasing and other things has to be changed. So remote electrical tilt, RET, can tilt the antenna in real time, which can be used for changing the capacity and coverage during the rush hours. It is easier for fine-tuning the soft handover and changing or expanding existing network. So today, most of the base station antennas, they have the provision of tilting, changing or reconfiguring the tilt remotely from a distance. And then vertical beam shaping, this is also important parameter, because as we told that in the horizontal coverage, we have already discussed how we can find out what should be the uh, beam angle and then how much tilt you will require. In the vertical plane, what should be the beam size, that also can be determined. And in vertical pattern, special interest is put on rapid roll-off above the beam peak to a deep wide null. So it should fall off sharply. Suppression of the first upper side lobe. So these are side lobes are the spurious emission in the and it may interfere with the other system, and you want to put the first side lobe, suppress it, slow roll off and null fills below the beam peak, and the change beam should not fall sharply, because as slow as possible. So we want slow roll off and electrical downward beam tilt, and the beam tilt should be adjustable electrically. Now, why these things are needed? A rapid roll off above the beam peak and suppression of the first side lobe is to minimize the interference into co-channel cell, and slow roll off and null fills below the beam peak ensures coverage very close to the cell site. But if when you are looking at an angle and you optimize your beam in such a way the entire cell is covered properly. Now, these are some of the design considerations that are usually taken up when designing the base station antennas. And I think I've covered all the major issues, and thank you for attending this session, and I can take up few quick questions if they are there.
Thank you, sir. So participants are requested to please put your queries in the Q&A section. Or in case if the participants, if you have any query, you may raise your hand as well in the platform. We may unmute you and you may interact with sir.
Yeah, and also I would like to interact because some time is there. I would like to interact with some of the participants if they want. Being a coordinator of this program, it is important to have some words. So if anybody wants to discuss something, please raise your hand and we can have a discussion.
So participants, please raise your hands. We will unmute you and you may have a discussion with sir.
I could not put the references in the slide. Today I was a little bit occupied with another meeting. When I will share the slides with the E&ICT Academy, which will be finally put into the program website, there I will put the references that has been consulted for preparing this talk. Okay.
Okay, sir. Any of the participants, if you're having any doubt, please put in the Q&A section or please raise your hand.
So people must be tired of antennas. Since morning, there whole day people are attending sessions on antennas. Anybody want to discuss anything, any particular issues on antennas, whatever I could, to the best of my understanding, I will try to answer your queries.
Sir, no questions yet. Yes, sir. So one question, sir, how to analyze modes?
Modes where?
Yes, Miss Taruna, if you can please elaborate the question.
You can unmute her and she can ask. Modes in a web guide?
Sir, we are not being able to unmute her. Sir, like how to analyze modes inside inside rectangular. Ma'am, please write the full question so we are not being able to understand. And if you want, you may unmute yourself also. We are not being able to unmute you. So the next question is how to find the cross polarization.
Yeah, cross polarization is the power that goes to a polarization which is undesired. Suppose I make an antenna which is linearly polarized, and suppose it is to transmit power with X polarization oriented along X. What we mean by polarization usually is the direction of the electric field. So I have the EX component. And so if it is a purely a X polarized, then I should not have any UI component. So if you do the measurement, if you want to do the measurement, suppose I radiate from a antenna which is very purely vertically polarized, and then I put my receiver which is also vertically polarized. If I rotate and put it horizontal, and if I get some power, that means my antenna, the receiving antenna which I am measuring, it is not purely vertically polarized. It has some horizontal polarization also it picks up. So in that way, you can actually find out whether it picks up the signal uh, from the undesired polarization, and their ratio we call the cross polarization, often expressed in dB. So a practical antenna, say if we say that the cross polar separation or cross polarization is better than 30 dB, we means that this Y component, even if it is received, it will be 1,000 times uh, smaller than the desired one. So in that way, you can actually define the cross polarization. Do I answer your question? Cross polar component is a waste of power. If you have high cross polarization, you want to transmit power in the X, but power is going towards Y polarization, which will not be picked up by your antenna. And many a times this is important because we provide polarization diversity. What does it mean? From the same antenna, suppose I want to transmit one signal which is X polarized, another is Y polarized. So I transmit both the signal. Now, when I am receiving, suppose I am receiving X polarization in one place, Y polarization is another place. If my antenna is not having good cross polar isolation, it will pick up both. Along with X, it will pick up some components of Y, which is undesired. So that's why we need to design systems where the cross polarization is very, very low. Cross polar component is suppressed, and cross polar suppression techniques are used in many of the antenna designs.
Thank you, sir. Taruna ma'am, we have unmute you. If you can please put your query. Taruna ma'am. Taruna ma'am, आपका.
Probably any other question?
Yes, sir. Sir, what's the difference between massive MIMO antenna and smart antenna?
Massive MIMO, it must have been explained. This is a different philosophy. Smart antenna is an antenna system where each antenna is connected with a separate radio chain. I mean to say, when I say radio chain, if it is a transmitting antenna, then you have a power amplifier, you have a mixer, and every antenna has its this. If it is a receiving antenna, it will have an LNA and a mixer for down conversion. So a smart antenna will have every antenna which is connected with a radio chain, and then once you bring the signal down to the baseband, you can weight those signals by multiplying it with complex weights, both magnitude and phase. And if you do that, your beam will change direction. Now, why it is smart? Because we put some adaptive algorithm also, so that the beam direction can change automatically towards a particular predefined direction and maximize the signal reception. You can actually increase the range of the antenna by co-phasing from all the elements if your the signal, which if you want to increase your range, similarly you can decrease, so you can adjust the range that is covered by it. You can position the beam, you can track some user by estimating the angle of arrival of the signal from that users. So you can do all these things. So this is the smart antenna system which actually people try to use in the wireless communication or mobile communication system, mostly third generation onward. There is another less complex version of it used called a fixed beamformer. So a smart antenna is an adaptive beamformer. It can adapt. There are some weight update algorithms. Lots of statistical signal processing concepts are applied. At the RF level, there is the beamformer like Butler matrix. So you can throw the beam in some specified location by using this type of system. So both way it is possible. Butler matrix also will provide you actually some phase shifter, and you can change the beam direction. So these are called fixed beamformer, and adaptive beamformers are known as smart antenna. Now when it comes to massive MIMO concept is slightly different. What it means that even if you are using MIMO, you will get signal variation at the cell edges. You will not get the same type of services or signals quality when you are in, say, in the middle of the cell and when you are at the cell edges. So then it was that seminal work. It showed that if you use a large number of antennas, then the variations in the channels can be avoided, and even a single antenna system user equipment will get good signal even at the cell edges. So I think there was a complete session on massive MIMO. They have discussed the theory, this channel hardening and all other things. Uh, so conceptually, this is different. Smart antenna is you rotate your beam and other things, and you track the user. You can create multiple beams together, but the number of antenna elements will not be that high. But here in massive MIMO, you require very large number of antenna elements, and you try to overcome the variation produced in the channel by using larger arrays. Any other queries?
Yes, sir. So the next question is, if voltage standing wave ratio is very large, what happens to the base station antenna?
Voltage standing wave ratio, it may be very large because of two things. For open circuit, the magnitude of reflection coefficient is 1. Also, for short circuit, the magnitude of reflection coefficient is 1. And for both the cases, standing wave ratio is defined as 1 plus mod of gamma divided by 1 minus mod of gamma. In both the cases, when mod gamma tends to unity, VSWR becomes very high. So immediately you know that somewhere some short circuit has happened or somewhere some open circuit has happened. Your signal is either not going into this or into the system at all, or your signal got short circuited. So by VSWR changing, you know that the operating conditions are not being followed, and you can actually check where the fault lies. As such, there may be short circuit in some path. So antenna element signal might not be reaching the antenna element at all. Or the feed lines connecting the antenna element might have broken. So the VSWR, if you are monitoring, you will see a large VSWR.
Yeah. Thank you, sir. So the next question, so can we design dual band patch antenna with different polarization?
That you will have to, I cannot, oh, it is possible. It is possible. Dual band polarization, same polarization. If you dual band antenna with different polarization, that you can do. You can have the radiating elements placed, the these things optimized. It is off-end solution I cannot provide. It is a design thing. The feasibility will have to be seen. How you are going to design. Suppose you stack two antenna elements. I give you a simple solution. A rectangular antenna, another smaller rectangular antenna. You stack them. One is designed for, say, X polarization, other is oriented in a Y polarization. And because their sizes are different, then you will have different operating frequencies. So you can have this type of an antenna arrangement, and you can have different polarizations, and the antenna, overall the antenna is operating in two bands. So it is possible, but with single element, if you want to do that, it will be difficult. You can have side by side elements, or you can do stacking, and then you can adjust the feeding. It is doable.
Thank you, sir. Yes, Taruna ma'am, you may please put your query. We have unmuted you.
Okay, thank you, ma'am. Thank you, Firoza ma'am, for such a smooth conduction. Thank you very much. And sir, good afternoon, sir. Please
Good
accept
afternoon.
my greetings.
Yeah, please.
Sir, please excuse me if I ask something irrelevant. I'm a Navy student in antennas. Recently, I have started working with DRA, dielectric resonator antennas.
Yes, yes, yes.
Sir, my question is very primitive. I am unable to figure out the modes. See, suppose I have made an antenna, a rectangular DRA. The geometry I'm working with is rectangular. I made some changes in the basic microstrip fed. I put a stub into it. I try to cut a slot inside to make capacitive reactance working. So the modes, my first and basic problem is modes. I'm unable to analyze modes. Sir, the patterns, the which I can see, the electric field configurations that I can see inside DRA. Uh, suppose the dominant mode I'm talking about is TE111 in my DRA. Second mode is TE113. So how do we get to know that this mode has come into action? With the help of impedance graph?
field pattern, if you can plot the field vector field patterns, you can see what is the closest mode. See, DRI is essentially a resonator, is not it? It is a
Yes,
leaky
sir.
it is a leaky resonator, and the
Yes, sir.
mode designations are also done accordingly. Now, if you are taking a DRA, the height is very small, then people also use this type of designations, TM11 delta mode, like that. Huh?
Yes, sir. Yes, sir.
Yeah. So you will have to do a plot of the. If you are using some simulator, I think you are using for design.
Yes, sir. Yes, sir.
So please try to plot the field pattern, and from the field pattern, then you will get an idea that what is the closest operating mode it is. And also, uh, let me, uh, what is after all a mode? It gives you the variation, is not it? So if it
Yes,
is a
sir.
rectangular antenna, if I say 101, that means I have a half wave variation in one, no
Yes, sir.
variation in, and another half wave variation
In
in the
another
Z.
dimension.
Yeah. So,
Yes.
so this is where we designate the mode. Please consult this book by Mangia's book. If you consult there, they
R.K.
have,
Mongia, sir.
yeah.
Yes, sir.
So,
R.K. Mongia, sir. Sir, where I'm stuck is, sometimes there is mode merging when you are specifically talking about broadband antennas,
mm,
wideband antennas, ultra wideband antennas. So what happens
mm.
is modes are being generated and they are amalgamated to get you a wide impedance bandwidth. Huh? So at the end, see, suppose first TE11 mode is being generated, then TE113 mode is generated, and afterwards I'm failed to recognize because there is so much of amalgamation happening. The merging of mode is happening in such a manner that there are no distinction in the
So,
modes.
so you are discussing a research problem which I'll find difficult to actually answer. Uh,
So that's why
you
I
see,
asked you to excuse me
no, no,
because I am David and I'm
each mode from a circuit point of view, how will you represent? It is a resonator,
yes, sir.
and then when you have a multi-mode, that means there are multiple resonant frequencies,
Yes,
and
sir.
that means multiple resonators. And what you are telling amalgamation, this is actually, we call it staggered. So when you have two resonators which close by resonant frequencies, if you take the overall, because your feed element is the same, so
Right, sir.
its response will broaden. So this is what is done. So in a multi-mode, these things, we try to generate nearby modes deliberately so that their frequency differences are small, and over a band of frequencies you get a wider frequency response and the pattern remains almost same.
True,
Now,
true.
how many modes are getting generated? That is, if these modes are very close to each other, because you will have to plot those field patterns at respective frequencies. Uh, Maybe sometime offline I will take you and I will connect you to one of my research student, Anup, who works in dielectric resonator antennas. So
Oh,
he will
that would
be
be very nice of you, sir.
okay.
Thank you so much, sir. Thank you.
Yeah, yeah. Firoza has the number of Anup, so you can be in touch with Firoza. She can
Okay.
connect you to Anup, and he works with dielectric DRS of different geometries, and this he can help you in identifying the modes. Okay.
Okay, sir. Thank you very much. It was really a profound experience. Thank you very much, sir.
Thank you. Thank you.
Thank you, Firoza ma'am.
Yeah.
Thank you very
Thank you.
much.
Thank you, Taruna ma'am. Thank you, sir.
Okay.
Yeah. And so we have the last question, sir. So
Hmm.
what is the difference between radiation pattern of isotropic and omnidirectional antenna?
Isotropic radiator is a fictitious radiator, uh, which radiates uniformly in all directions. So it is a spherical. And omnidirectional may be a omni pattern in one plane, not necessarily omni in the other plane. For example, if you take a dipole has a uniform coverage along the horizontal, but vertical, this is not. But if it is an isotropic radiator, then it will radiate equally in all directions. So you will get a pattern looking like a football sphere. Okay.
Thank you, sir. So all the questions were addressed. So
Can
thank you, sir,
I?
for the informative session. Yes, sir. So should
So can
we
I?
end the session?
Yeah. Thank you.
Okay. Thank you, sir. Thank you to all the participants. The materials will be shared in Drive as day-wise material as always shared. So please check the Drive link for the material and please connect tomorrow by 9:30.
Okay.
Thank you.
Thank you.
Thank
Thank
you.
you.